Okay, this video we're going to talk about quantifiers and negation. So there are two quantifiers that we'll be working with, and they're the for all quantifier, and there's shorthand notation for that. It looks like an upside down A. And the other quantifier is the existential quantifier. There exists, and the shorthand logical notation for that looks like a backwards uppercase E. So I want to take you through a few examples where we think through the, we'll practice translating sentences into logical statements back and forth. We will try to think about whether the statements are true or false, and we'll think about how to negate them. Okay, let's go. So the first statement is, for every integer x, 0 plus x is x. So that's written as a sentence. Let's write it in logical notation. So the logical version of this looks like, for every x in z, 0 plus x equals x. These two things have exactly the same meaning. And when you turn in work for me, what I'm going to want in your writing is the kind of statement that looks like a sentence, okay? Which isn't to say that it can't have some logical notation in it. Sometimes writing out everything in words gets really hard to parse, and the logical notation can sort of draw our attention to what to pay attention to and help us take some of the cognitive load off us. And part of the job of this course is to help you find that balance in your writing, when to use words, when to use logical notation and equations, and how to do it in a way that makes it easier for your reader. Okay, so is this statement true or false? It's true. 0 plus x is equal to x for all integers x. Let's think about what the notation would be, negation would be. So if we're negating the statement, for every x that's an integer, 0 plus x equals x. So there's a cheap way to do it, and we're not going to do the cheap way. Okay, so the cheap way is to say it's not true that for every x in z, 0 plus x is x. So why aren't we going to do that? So when you have negative words in the sentence, it puts the cognitive load on your reader to sort of figure out puzzle out what you really mean. We want to process things for the reader as much as possible so our writing is clear and easy to understand. That's the point. Good communication. Okay, so this is a statement that says something is true for every integer. If that statement is false, that statement is false when it's true for even just one integer, okay? So in logical notation, we might write the negation is something like this. There exists an integer x, and I'm going to use s dot t dot for such that 0 plus x is not equal to x. So this is equivalent to the negation of the statement. And if I wanted to write the statement in words, I might say, for some x that's an integer, 0 plus x is not equal to x. So in writing, the words there exists and for some are sort of interchangeable. Okay, so let's look at another example. Here we have an example that uses the there exists construct. So there exists a real number x such that x plus 5 is 0. We can rewrite that in logical notation. There exists an x in R such that x plus 5 equals 0. Okay, is this true or false? It's true, right? Because the number x such that x plus 5 is 0 is negative 5. So this is a true statement, just like the other one was true. Maybe I didn't write that. This is true, and this one is also true. We can take x equal to negative 5. What does the negation look like? So if we wanted to negate the statement, there exists a real number such that x plus 5 equals 0. Well, so that statement is false if we can't find any real numbers that make x plus 5 equals 0. In other words, we could say for every real number x, when I look at the equation x plus 5 equals 0, it's false. So for every x in R, x plus 5 is not 0, right? I can't find a solution of that equation. In words, we might say for all real x, x plus 5 is not 0. Okay, and one of the things that's going to be really important both in future math courses and computer science courses is this understanding, this fluidity, to become fluent, going back and forth between logical notation and sort of more, I don't know, colloquial writing, and understanding how to mix the two really effectively to get your meaning across in a way that's as clear as possible. Okay, so let's look at some more examples. These are a little more complicated. They have a mixture in them of the two existential quantifiers. Okay, so the first one, there exists an integer a such that for every integer x, a plus x equals x. So is this true or is this false? Well, it's actually related to the very first example, isn't it? So in the very first example, we had 0 plus x is x for all real x. And so the a that we're asking, whose existence we're wondering about in this example, is the number 0, right? So this is a true statement. Oops, still, I need to get my pen back. This is a true statement. We could take a equals 0, and that's the number that exists that makes it true. We could rewrite it in logical notation. There exists an integer a such that for every integer x, a plus x equals x. We could also look at the negation of this statement. So let me try to see if I can do something fancy. Hold on. If I take this and I do this and I duplicate it, whoa. So I've duplicated it. And now what I want to do, okay, that was my fancy stuff. Now I'm negating it. What does it look like when I negate it? Well, so this statement says, there exists an a such that for all x, a plus x equals x. It's not true if for all integers a, there exists some integer x such that a plus x is not equal to x, okay? So the negation, if I write it as a sentence, would be for all integers a, there is some integer x with a plus x not equal to x. All right, let's look at the next example. So for every integer x, there exists an integer y such that x plus y is 0. So this one reminds me of our second example, right, where there we had looking at the equation x plus 5 is 0 and wondering if there exists a solution there. Here we're looking at the equation x plus y equals 0 and wondering if there's a solution for x, okay? So it's true This is a true statement, just like the other one. And the y that we're looking for would be y equal to negative x, makes that true. If we wanted to write it in logical notation, we could say for every integer x, there exists an integer y such that x plus y equals 0. Oops, I didn't want to do that. Let's see if I can do this again. I'm going to do this little copy paste thing so I can negate it quickly. So when I negate this statement, what I get, so this statement says for all integers x, there's some y, so that x plus y is 0. It's not true if for some x, so there exists an integer x, such that for every integer y, x plus y is not 0. So I could rewrite that in words as there exists some integer x such that for all integers y, I gotta move this now, such that for all integers y, x plus y is not 0. All right. And now in this last example, I wanted to do it with you because it's playing around. It's very similar to the example above, right? What I've done with these two examples is I have switched the order of the two clauses. And what you'll see is it really changes the meaning. So it changes the meaning. And it's not the negation, so it's a different thing entirely. So this statement, there exists an integer y such that x plus y is 0 for every integer x. This is false, right? This is not something that's true. If you have an integer y and x plus y is 0, there's only one x, but that's going to work for it. It can't be true for all the x's, right? In logical notation, this is there exists an integer y such that x plus y equals 0 for every integer x. And then if I want to negate this statement, so maybe I just will, instead of copy pasting, just write the negation is for all integers y, there exists some integer x such that x plus y is not equal to 0. Okay, so for all y and z, there is some x such that x plus y equals 0. All right, thank you for listening.